Oh, class. Here's another example. Building confidence intervals from beginning to end and transferring the information onto the appropriate drawing. It's a different set of information this time. So if you want, go ahead and pause this video. Hopefully it's high def enough that you can get the information and it won't be, hold it really still. So when you pause. The information I'm asking you to assume is a mean of 17, a standard deviation of 4, a sample size of 20, and the task at hand is building 80% confidence intervals. So once again, a mean of 17, standard deviation of 4, and a sample size of 20, and we have to build 80% confidence intervals. So I followed the exact same steps and procedures that I did last time. Here, I repeated the information you already know. Mean of 17, standard deviation of 4, sample size of 20, 80% confidence intervals. The first thing I did was calculate the sample's standard error S sub x bar. The standard error equals the standard deviation, which we already know, 4, divided by the square root of n. We already know n, 20. I simply substituted the information and came up with what I hope is the correct number. Standard error equals 4 divided by the square root of 20. Standard error equals 4 divided by 4.472. That's the square root of 20, rounded appropriately. Standard error equals 0.895. So boom, I have the sample's standard error. And by the way, I want to pause for just a minute and mention that that number, 0.895, that is a descriptive statistic for this imaginary sample. Again, that standard error is simply another measure of variability, just like the range, just like the interquartile range, just like the variance, just like the standard deviation. Now we have another measure of dispersion that we're calling the standard error for the sample. The standard error for this sample is 0.895. Again, just simply taking the standard deviation divided by the square root of n. The next thing I did, this portion right here, the next thing I did was consult the t-table to find the appropriate t-value from the t-table. So I took my handy-dandy t-table and I found 19. I'll double check my work with you live on the air. Not really live, but let's see, sample size of 20, which means 19 degrees of freedom, and 80% confidence intervals, which means my t-value is 1.328, right? So I placed that right here. T equals 1.328, and then parentheses, degrees based on, where did I get that number? Where did I pull that number from? I pulled it based on degrees of freedom of 19 and 80% confidence intervals. The degrees of freedom, the task at hand. The degrees of freedom and the task at hand. Then I used my formula for the lower limit and the upper limit simply to substitute the appropriate information to find the actual intervals, the actual confidence intervals for this problem. Lower limit equals the mean minus a value from the t-table times the standard error for the sample. We already know all this information. Lower limit equals a mean of 17 minus 1.328, that came from the table, times 0.895. That's the, yes, 0.895. That's the standard error for the sample. Lower limit equals 17 minus 1.189. That's simply the t-value from the table times the standard error for the sample. Lower limit equals 15.811. Boom, that's our lower limit. We're half done. Upper limit equals the sample mean plus a t-value from the t-table times the standard error for the sample. Upper limit equals 17 plus 1.328, that came from the t-table, times 0.895, that came from our calculation of the sample. Upper limit equals 17 plus 1.189, our upper limit equals 18.189. Boom. 80% confidence intervals for this problem is 15.811 to 18.189. Let's pause for a moment and talk about what that interval means. What that interval is saying. Here's the story. Remember the story? The story is we have a sample, which means we have error. We calculated a mean, 17, which means we have an estimate, what we hope is a good estimate, for the population from which the sample came. However, because we sampled, we know that this number contains error. But after our Mathemagic, we now can say 17 might not be the correct population parameter, but we can be 80% sure, 80% confident, we can be 80% sure that the true population mean falls somewhere between 15.811 and 18.189. Now, let's transfer this information to the appropriate, or in the appropriate fashion, into the drawing. Okay? Perhaps it will come as no surprise that I started with the bell-shaped curve. What's the task at hand? The task at hand is building 80% confidence intervals, which means the middle portion is 80% and each of the tails is 10%. 10 plus 80 plus 10 is 100. I'm going to put the legend at the top. The legend is n equals 20, which means degrees of freedom equals 19. Our task at hand is 80% CI, confidence intervals, CI. Excuse me, and our t-value is 1.328. I'll show it to you again in a second here. I put my dotted line down the middle as well. Again, I like to see that there. 80% in the middle, 10% in each tail. The legend, you've been working with this if you've been working along with the math. N of 20, degrees of freedom of 19, 80% confidence intervals means a t-value of 1.328. Now, all I have to do is add my t-value. First thing I'll do, I guess, is add my t-values. T equals negative 1.328 on the left side. T equals positive 1.328 on the right side. Again, that t-value, 1.328, or negative 1.328, positive 1.328, that information came from the table. Degrees of freedom, 80% confidence intervals. I'm going to place a t of what in the middle? What goes in the middle? A t of 0. Cooking with gas now. And then last but not least, I'm going to put my mean of 17 in the middle, and I'm going to put my upper limit from our math of 18.189 on the lower end of the abscissa, and our lower limit of 15.811 on the left. Boom. That's what that looks like. What that's saying, again, it's the same story you've already heard. A mean of 17 may or may not be accurate, may or may not be a good estimate of the population from which it came. 17, a mean of 17 may or may not be a good estimate of the population from which it came, but we are now 80% confident that the true population mean falls somewhere between 15.811 and 18.189. Shoot, can't find it. There we go.